13.8 billion years ago, the universe exploded into existence. Space, time, matter, energy, all of it, born in a single instant. We call it the Big Bang, and for decades science told us there was no before. Time itself started there. That story has cracked open. Scientists are now finding physical evidence, real signals baked into the oldest light in existence, that suggest something was here before the bang fired. Ancient patterns, circular echoes, structures too ordered to be accidents. We are going to examine what left them, what theories explain them, and what it means for every assumption you have ever made about reality. If you enjoy the journey, subscribe. We are going to need you for what comes next. Brace yourself. We begin. Every culture that ever existed invented a story about how everything started. And for most of human history, science had nothing better to offer. Then, in the 20th century, physicists cracked the problem open. They traced the expansion of the universe backward, like rewinding a film, and landed on a single point, a moment before which, officially, there was nothing. No space, no time, no before. That answer held for decades. It was clean. It was teachable. It became the opening line of every astronomy textbook on Earth. Then the data started disagreeing. The first crack appeared quietly. Scientists studying the oldest light in the universe, a faint glow that fills every direction of the sky called the cosmic microwave background, noticed something they could not explain away. Patterns. Faint, circular ripples embedded in that ancient light, arranged in ways that standard Big Bang theory said should not be there. The universe at its birth should have been chaotic, foamy, random at those scales. These patterns were structured, deliberate-looking. One of the greatest living mathematicians looked at those patterns and made a claim that stunned the scientific community. He said those circles were not random noise. They were fossils. Fossils of events that happened before the Big Bang. Pause on that. Before the Big Bang. His name is Roger Penrose. He is a Nobel Prize-winning physicist, not a fringe thinker, and his argument rests on real mathematics, real data, and a framework so audacious it rewrites the shape of time itself. His theory is called conformal cyclic cosmology, and it proposes that our universe is one chapter in an infinite book. Each universe is born, expands, grows cold, and then passes through a kind of cosmic membrane into the next universe, which we experience as a Big Bang. The circular patterns in the ancient light, Penrose argues, are the dying screams of black holes from the universe that came before ours. When black holes in a previous universe evaporated over unimaginably long timescales, they released their energy in spherical pulses. Those pulses, according to this theory, left faint imprints that survived the transition between universes and are still readable today, burned into the first light of our own cosmos. Scientists call these imprints Hawking points, named after Stephen Hawking, whose work on black hole evaporation underpins the whole idea. Now, the scientific community is divided. Several research teams have searched the cosmic microwave background data and reported they can find those circular patterns, confirming Penrose's claim. Other teams have searched the same data and concluded the patterns fall within the range of random noise. The debate is active. The question is genuinely open. But here is what is settled. The cosmic microwave background exists. Its patterns are real and measurable, and some of those patterns remain unexplained by standard cosmology. That gap is where the story lives. We are standing at the edge of the known universe, not in space, but in time, and peering through a faint glow at something that should be invisible, something that predates everything we have ever measured. And it is leaving us messages. The question is whether we are smart enough to read them. The cosmic microwave background is the oldest signal we can detect. Every answer about what came before the bang runs through it. And when you look at it closely, you realize it is stranger than anyone first admitted. Imagine the universe as a room that was once so hot, so dense, that light itself could not travel through it. Every photon fired in every direction immediately slammed into a particle and scattered. The entire cosmos was opaque, like trying to see through a wall of solid white fire. That lasted for roughly 380,000 years after the bang. Then, as the universe expanded and cooled, something unlocked. Electrons bonded with protons for the first time. The fog cleared, and every photon that had been trapped in that burning plasma streamed outward all at once, in every direction, across the entire universe. That light is still traveling. Right now, in this moment, ancient photons from that first clearing are passing through the walls of the room you are in. They are passing through you. They have been traveling for over 13 billion years, and they carry, encoded in their temperature, a snapshot of the universe at its earliest readable moment. Scientists call this the cosmic microwave background. It was confirmed accidentally in 1965 when two engineers at Bell Labs in New Jersey pointed a large antenna at the sky to test satellite communications and kept picking up a persistent hiss from every direction they aimed. They thought it was pigeon droppings on the antenna. They cleaned it. The hiss remained. It was the echo of creation. When satellites mapped this ancient light in exquisite detail, what they found was mostly uniform. The temperature of this light across the entire sky varies by only about 100 thousandths of a degree. That near-perfect smoothness is already a mystery, because regions of the sky that show the same temperature should never have been in contact with each other. The universe expanded too fast for them to have shared heat, and yet they match almost perfectly. That problem has a name: the horizon problem. And it is one of the reasons physicists started looking for something that happened before or during the very earliest moments of the Bang. But the smoothness is only part of the story. Embedded within that near-uniform glow are tiny fluctuations, regions fractionally hotter or colder than their neighbors. Those fluctuations are the seeds of everything. Galaxies, clusters, superclusters, the entire cosmic web grew from those tiny temperature differences. As slightly denser regions pulled in more matter over billions of years. The fluctuations match what inflation theory predicts almost perfectly. Almost, because scattered across the sky there are anomalies. A cold spot in the southern sky larger than it should be. Alignments of temperature patterns that seem to prefer a particular direction across the cosmos. And those circular rings that Penrose identified. Standard cosmology has explanations for some of these. For others, it offers educated guesses. A few remain genuinely unresolved. Each anomaly is a potential window. And what some physicists see through that window is a universe that existed before ours, shaping ours the way a mold shapes what is poured into it. The light we are reading is 13 billion years old, and some of the information written inside it may be older than time as we know it. What wrote those patterns is a question that gets stranger the closer you look. Long before any anomalous patterns showed up in ancient light, careful physicists had already spotted a crack in the standard story. It was hiding in plain sight, inside one of the most fundamental laws of physics. The second law of thermodynamics says that disorder always increases. A coffee cup drops and shatters. It never reassembles itself. A drop of ink spreads through water and never gathers back into a drop. The universe moves in one direction, from order toward chaos. Scientists measure this tendency with a quantity called entropy. High entropy means maximum disorder, maximum randomness. Low entropy means everything is arranged in an unlikely, structured way. Here is the problem. At the moment of the Big Bang, the universe had extraordinarily low entropy, impossibly low. Physicists have calculated how ordered the early universe was. And the number they arrive at is so improbable that if you tried to write it out, the exponent alone would fill every book on Earth. Picture a perfectly shuffled deck of cards spontaneously arranging itself into perfect numerical order by suit. Now picture that happening simultaneously across every deck of cards in every casino in every city on Earth. And then multiply that improbability by a number so vast it has no name. That is how ordered the early universe was at its birth. The second law says systems move toward disorder. So the Big Bang began at the most ordered state in our universe's history. That raises an immediate, uncomfortable question. How did a random explosion produce something so precisely organized? Standard cosmology has a partial answer involving inflation, a brief period of extreme expansion right after the Bang. Inflation smoothed things out and explains the near-uniform temperature of the sky. But inflation does not fully explain why entropy was so low to begin with. It pushes the question back a step. The physicist Roger Penrose has spent decades arguing that the low entropy of our universe's birth demands an explanation that inflation alone cannot provide. His argument is that the Big Bang was set up, that the conditions were prepared by something prior. In his framework, the previous universe ended in a state of maximum entropy, completely cold, completely dark, all matter dissolved, all black holes evaporated. And paradoxically, that state of maximum disorder transforms mathematically into something indistinguishable from the low entropy starting conditions of a new Big Bang. A universe dying of exhaustion becomes, through a mathematical transformation, the perfectly ordered starting pistol for the next universe. This is confirmed mathematics. The specific geometry works out. What remains a theory is whether our universe actually emerged this way. But the second law problem is real, documented, and taken seriously by physicists across the field. The crack was always there. The data from the sky just made it impossible to ignore. And there is something else hiding in those early conditions that should unsettle you further. The universe at its birth was tuned. Every constant, every ratio of forces, every dial of nature was set at values that allow stars, atoms, and life to exist. Change any one of them by a fraction, and the cosmos collapses or flies apart before a single star forms. That level of fine-tuning has its own explanation problem, and some physicists believe the answer lies in what came before. In the 1980s, a physicist named Alan Guth proposed something radical. He said the universe, in the first sliver of its first second, did not expand at a normal rate. It inflated, exponentially. A region smaller than a proton blew up to roughly the size of a grapefruit in a fraction of a second, so small it has no name in everyday language. That idea, called cosmic inflation, solved several problems overnight. It explained why the sky looks so uniform in all directions. If everything we can observe today was once squeezed into a region smaller than an atom, then all of it would have been in contact, sharing temperature, before inflation stretched it apart. The uniformity is a relic of that intimate contact. It explained the flatness of the universe. Inflation stretched space so dramatically that any initial curvature became undetectable, the same way a balloon blown up to the size of a planet would appear flat to anyone standing on it. And it explained the fluctuations. The tiny temperature variations seeding all structure in the universe correspond almost perfectly to quantum-scale ripples that inflation would have stretched from subatomic sizes to cosmic ones. The evidence for inflation is strong. The predictions match the data with striking accuracy. Most cosmologists accept it as the best current model of the universe's earliest moments. But here is where the ground shifts beneath you. Inflation has a problem it cannot solve from within. The inflating field, the energy source driving that exponential expansion, had to come from somewhere. Something had to set it in motion. Standard cosmology places the beginning of inflation at the very start of time, which means the question of what existed before inflation is the same as asking what existed before time. And inflation, if it started, tends to keep going, eternally. This is the core of a concept called eternal inflation, developed by physicists including Andre Linde. In this model, the inflating field never fully stops everywhere at once. Pockets of it decay and cool, producing local big bangs like bubbles, forming in a boiling pot. Our universe is one of those bubbles. The inflating field surrounding us is still going, right now, and other bubbles are forming constantly at a rate we can never track. The universe we live in is a bubble, a local event inside a larger, perhaps infinite inflating field that had no beginning in the way we normally think about beginnings. That should make you pause, because if eternal inflation is real, then the Big Bang was an eruption inside something that was already there. Our origin was a local event, not an absolute one, and the question of what came before shifts from philosophy to physics. The field that spawned us may have existed for an eternity before we appeared. It may be generating new universes right now, each one unreachable from any other, each one with its own physical laws, its own constants, its own version of what the Bang looked like. We are not at the center of creation. We are a bubble in an ocean we will never see, and the evidence for what that ocean looks like may already be in our hands. Every time a new universe bubbles out of the inflating field, it starts with different conditions. The laws of physics in our universe feel permanent, like the rules are carved into the foundations of reality. Gravity pulls, light travels at a fixed speed, electrons have a fixed charge. These values feel inevitable. They are not. In the framework of eternal inflation, each bubble universe that forms inherits a random configuration of physical constants from the inflating field. Most of those configurations produce universes that are instantly hostile to any kind of structure. Some collapse back on themselves in microseconds. Some expand so fast that matter never clumps together. Some have no atoms at all, because the force ratios that allow protons and electrons to bond simply do not exist in that configuration. A tiny fraction of those bubble universes happen to land on constants that allow stars to form, elements to build up, and eventually chemistry complex enough to think about itself. We are in one of those rare configurations, which raises an unsettling possibility. The reason our universe seems fine-tuned for life may have nothing to do with design. It may be selection bias. Only in universes where the constants work out can there be anyone around to notice how perfectly everything fits. This is the anthropic principle applied to the multiverse, and it is a genuinely scientific argument, uncomfortable as it is. But the multiverse carries a problem that its critics never let go of. It may be untestable. If other bubble universes exist beyond our observational horizon, separated from us by an inflating barrier, we can never detect them directly. And a theory that makes no testable predictions sits uncomfortably close to philosophy. Except, there may be one way to test it. If two bubble universes were ever close enough to brush against each other early in their formation, that collision would leave a mark, a specific circular imprint in the cosmic microwave background, a region where temperature and polarization deviate from their surroundings in a pattern distinct from normal fluctuations. Scientists have searched for these bubble collision signatures. Some researchers report candidate signals. Others find the same regions consistent with standard variation. The search is ongoing, and the specific patterns that would confirm a collision are well defined enough that future telescopes may be able to settle it. We may already have the fingerprint of a neighboring universe sitting in our data, waiting for an instrument sensitive enough to confirm it. The multiverse began as a philosophical inevitability of inflation math. It is becoming a testable prediction, slowly, imperfectly, but genuinely. And the idea that something larger than our universe existed before our bang is no longer science fiction. It is the logical consequence of our best theory of the early cosmos. But eternal inflation is not the only model that puts something before the bang. There is an older, stranger idea, one that does not require an infinite field or an endless sea of bubble universes. It requires something far simpler, a universe that bounced. Picture the universe running in reverse. Galaxies rush toward each other. Stars compress. Space shrinks. Everything that ever spread outward over 13 billion years collapses back inward, growing hotter, denser, more compressed with every passing moment. The Big Bang plays backward until it reaches a point of maximum density. Standard physics, specifically Einstein's general relativity, says that point is a singularity, a place where density becomes infinite, where the equations break down entirely, where space and time cease to have meaning, a wall beyond which physics cannot see. But general relativity is known to be incomplete. It breaks down at extremely small scales, where quantum mechanics takes over. And when physicists apply quantum mechanics to that collapsing point, something remarkable happens. The singularity disappears. This is the foundation of a framework called loop quantum cosmology, developed over decades by physicists, including Abhay Ashtekar. In this model, space itself is made of discrete chunks, the smallest possible units of volume, so small they make atoms look enormous by comparison. Because space comes in these minimum chunks, it cannot collapse to zero. There is a flaw. When a collapsing universe reaches that flaw, the crushing force of compression becomes a repulsive force, flipping the collapse into an expansion. The crunch becomes a bounce. The Big Bang was, in this model, a big bounce, the moment when a prior collapsing universe rebounded into expansion and became ours. The mathematics of loop quantum cosmology are self-consistent and well-developed. This is an active and respected area of theoretical physics. The bounce is not confirmed, but the underlying framework produces real, testable predictions about the structure of the early universe that the next generation of telescopes will be able to check. And here is what that bounce implies. The universe that collapsed into ours had a history. It had its own galaxies, its own stars, its own billions of years of evolution. It left behind, embedded in the moment of maximum compression and rebound, imprints in the primordial fabric of space. Those imprints would show up as specific signatures in gravitational waves, ripples in space-time itself, that would carry information about pre-bounce conditions. Gravitational waves from that era would be at frequencies far below what current detectors can measure. But planned future observatories would operate in exactly the range needed to catch them. We may be a few decades and a handful of instruments away from hearing the echo of the universe that came before us. And the bounce model carries one more implication that makes it feel personal in a strange way. If the universe bounces, it does so repeatedly. The cosmos before ours bounced from one before that. The chain may extend indefinitely in both directions. No true beginning, no true end, just an eternal rhythm of collapse and rebirth. Every atom in your body may have passed through that gateway before. Stand at the edge of what physics can describe, and you find a threshold with a name, the Planck scale. It is not a place, it is a size. Below 1 Planck length, roughly 10 to the power of negative 35 meters, the known laws of physics cease to function as we understand them. Quantum effects become so dominant that space itself stops behaving like a smooth fabric and begins to fluctuate wildly. Time loses its arrow. Cause and effect blur into a probabilistic foam. To give you a sense of scale, a proton is already extraordinarily small. The Planck length is roughly 10 million billion times smaller than a proton. You cannot approach it, measure it, or directly probe it with any instrument humanity has built, or could realistically build. The Big Bang happened at Planck scale conditions. That first critical instant is beyond the reach of every equation we currently trust. This creates a genuine scientific barrier. Everything we claim to know about the Big Bang is technically about what happened after the Planck era ended, roughly 10 to the power of negative 43 seconds after the bang. Before that threshold, our equations produce nonsense. Infinities, zeros in denominators, results that mean nothing physically. So when physicists talk about before the Big Bang, they are partly fighting against their own tools. The laws we use to describe reality were either created at the bang or became applicable only after the Planck era passed. Asking what existed before using those laws is like using a ruler to measure something smaller than the ruler's smallest marking. The tool breaks before the question gets answered. But physicists have a habit of refusing to accept broken tools as final answers. Two frameworks attempt to describe physics at and below the Planck scale: string theory and loop quantum gravity. They approach the problem differently and currently reach different conclusions. Neither is confirmed. Both are mathematically rigorous and scientifically active. What both agree on is this: the singularity at the Big Bang is almost certainly not physical reality. It is an artifact of using general relativity in a domain where it does not apply. The actual physics at that moment almost certainly involves quantum effects that smooth out the singularity, replacing a wall with a transition. A transition from what to what? That is the question. Some physicists argue that the Planck era itself contained the memory of a pre-existing state, that the quantum foam at the dawn of our universe was not random, but shaped by conditions from something prior. The low entropy problem from Chapter 3 appears here again, because even at Planck scale conditions, the universe was arranged in an improbably ordered state. Something set those conditions. The Planck scale is the keyhole through which all pre-bang theories must pass. It is the lock on the door to what came before. And different theories carry different keys. One of those keys comes from a place most people associate with abstract mathematics and invisible extra dimensions. And what it suggests about the origin of the bang is so visual, so strange, it is almost impossible to fully accept. String theory began as an attempt to unify gravity with quantum mechanics, the two great pillars of physics that refuse to work together in the same equations. It grew into something far larger, a framework in which the fundamental particles of nature are not points but tiny, vibrating strings of energy. And the universe exists not in 4 dimensions, but in 10 or 11. The extra dimensions are real in string theory's mathematics. They are simply curled up too tightly to observe at any accessible scale. For most of its history, string theory offered beautiful mathematics and almost no testable predictions. But in the late 1990s, a specific version of the theory produced something startling, a model of the Big Bang that requires nothing inside our universe at all. This model is called the ekpyrotic universe, from the Greek word for a great fire. Developed by physicists including Paul Steinhardt and Neil Turok, it proposes that our universe is a 3-dimensional membrane, sometimes called a brane, floating in a higher dimensional space. And it is not alone. Picture 2 vast, flat sheets suspended parallel to each other in a higher dimension, like 2 pieces of paper facing each other in the air, separated by a tiny gap. Those sheets are universes. They drift slowly toward each other through the higher dimension. And when they collide, the collision releases an enormous burst of energy across both surfaces simultaneously. That burst of energy is the Big Bang. Everything you see around you, every galaxy, every star, every atom of matter in existence, is the aftermath of 2 universe-scale membranes slamming into each other. The energy of that impact filled our brain with heat, radiation, and the seeds of structure. Before the collision, our membrane existed. It was cold, flat, nearly empty, and drifting slowly through higher dimensional space. It had a history, a past, a before. The ekpyrotic model makes specific predictions about the cosmic microwave background, particularly about a property called primordial gravitational waves. Standard inflation predicts a strong background of these waves. The ekpyrotic model predicts they would be nearly undetectable. Future gravitational wave observatories will measure this background, and the result will help distinguish between the 2 models. This is real science. The competition between inflation and ekpyrosis will be decided by data, not philosophy. And here is the detail that should stay with you. In the ekpyrotic picture, the cycle repeats. After our brain fills with matter and energy, it eventually cools, expands, empties out, and then begins drifting again. The other brain does the same. Eventually they meet again. Another Big Bang, another cycle. The universe is not born once. It is born over and over, in great collisions between membranes, across a higher dimension we will never directly observe. 2 sheets of reality, touching and sparking everything into being. The image is almost too large to hold. But what happens in the moments directly after the bang, in the first fraction of the first second, is where things get stranger still. The Big Bang did not produce the universe you see today all at once. In the first second after the bang, reality went through more transformations than in the following 13 billion years combined. Let us walk through it, because the sequence itself tells you something about what came before. At time 0, physics breaks down. The Planck era. No reliable description exists. After 10 to the power of -43 seconds, quantum gravity effects fade, and the inflating field takes over, if inflation occurred. The universe is still 1 trillion times smaller than a single proton. The temperature is incomprehensibly high, and every force of nature, gravity, electromagnetism, the strong and weak nuclear forces, all exist as a single unified force. At around 10 to the power of -36 seconds, inflation begins in most models. The universe blows up exponentially, doubling in size every unimaginably tiny fraction of a second, for a period that ends around 10 to the power of -32 seconds. In that brief window, the universe expands by a factor of at least 10 to the power 26. A region the size of an atom becomes larger than a galaxy. When inflation ends, the energy stored in the inflating field converts into heat and matter. This moment is called reheating, and it is essentially a second Big Bang of energy, flooding the universe with particles. At 10 to the power of -12 seconds, electroweak symmetry breaks. Electromagnetism and the weak nuclear force, once unified, split apart. The Higgs field switches on, giving particles mass for the first time. Before this moment, every particle in the universe was massless and traveling at the speed of light. At 10 to the power of -6 seconds, quarks cool enough to bind together. Protons and neutrons form. At 1 second, the universe is a hot plasma of protons, neutrons, electrons, and neutrinos. Neutrinos stop interacting with everything and stream freely outward. They are still streaming today, a ghost ocean of particles passing through the Earth constantly, carrying information about the universe at 1 second old. At 3 minutes, protons and neutrons fuse into the first light atomic nuclei, mostly hydrogen and helium. The ratio of hydrogen to helium produced in this window is measurable and predicted precisely by theory. Observations match the prediction. This is one of the strongest confirmations of Big Bang physics. And then comes the long wait, 380,000 years of an opaque, burning plasma, until the universe cools enough for electrons to settle into atoms, and the first light streams free. Every step in this sequence had to follow from the one before it, with extraordinary precision. The ratio of matter to antimatter, the strength of the strong nuclear force, the mass of the Higgs, all had to land at exact values. If any step had gone differently, none of the rest follows. And those initial conditions trace back to the moment the bang began, which means someone or something set the starting parameters, whether that someone is physics, a prior universe, or something we have no name for yet. The parameters were set before the first second ever ticked. The universe runs on numbers: the strength of gravity, the charge of an electron, the mass of a proton, the speed of light, the cosmological constant, the energy density of empty space. These values are measured constants. We did not derive them from deeper principles. We measured them, wrote them down, and built physics on top of them. And every one of them sits at a value that allows the universe to produce structure. Change the strength of the strong nuclear force, the force that holds atomic nuclei together, by a few percent in either direction, and atoms heavier than hydrogen either never form or instantly fly apart. No carbon, no oxygen, no chemistry, no life. Change the cosmological constant by 1 part in 10 to the power of 120, the most extreme fine-tuning known to physics, and the universe either collapses on itself before a single star forms, or expands so violently that matter never clumps together at all. 1 part in 10 to the power of 120. That is a 1 followed by 120 zeros in the denominator. The precision required is beyond anything a human mind can intuitively grasp. Physicists call this the fine-tuning problem, and it is a genuine scientific crisis with no agreed solution. 3 main camps have formed. The first says the constants are simply what they are, and asking why is like asking why the universe exists at all. Some questions may have no physical answer. The second camp points to the multiverse. If an enormous or infinite number of universes exist, each with randomly selected constants, then some of them will land on life-permitting values, by sheer probability. We are in one because we can only exist in one that works. Selection bias, not design. The third camp argues the constants were inherited, that the universe before ours had its own constants, and through the transition process, whether a bounce, a brane collision, or a conformal cycling, the new universe's constants were seeded by the old one. The fine-tuning is real, and it was set by a prior physical process. Each of these positions has serious physicists defending it. None is confirmed. All 3 have testable implications, at least in principle. But there is a fourth possibility that almost nobody talks about in mainstream discussions. What if the constants are not truly independent? What if a deeper theory, one we do not yet have, shows that all these numbers fall out of a single equation, the way the shape of a snowflake falls out of water's molecular geometry? String theory attempts this. Its landscape of possible solutions numbers around 10 to the power of 500, each representing a different configuration of constants. The hope is that physics, not chance, selects the specific solution we inhabit. That hope has not yet been realized, but the search is ongoing. What is certain is this: the dials were set. Someone or something set them. The evidence is written in the survival of every atom in the universe, and the most direct path to understanding who, or what, did the setting runs directly through whatever existed before the bang. The universe is not just expanding, it is accelerating. Every galaxy is moving away from every other galaxy. And that movement is speeding up over time, as if something is pushing space apart from the inside. Physicists discovered this in 1998, and it overturned the dominant expectation that gravity would eventually slow expansion down. The force driving acceleration has a name: dark energy. And that name is essentially an admission of ignorance. We have no idea what dark energy is. We know how much of it exists, roughly 60 to 8% of the total energy content of the universe. And we know what it does: accelerates expansion. Beyond that, the mystery stands. The leading candidate is the cosmological constant, a term Einstein originally inserted into his equations to keep the universe static, then removed when Hubble discovered expansion, famously calling it his greatest blunder. When physicists applied quantum mechanics to empty space, they found it should be teeming with energy, virtual particles flickering in and out of existence. That quantum vacuum energy should act exactly like the cosmological constant. The problem is the amount. Quantum mechanics predicts a vacuum energy roughly 10 to the power of 120 times larger than what we actually measure. This is the largest discrepancy between a theoretical prediction and an observation in the history of science. Something is cancelling almost all of the predicted vacuum energy, leaving only a tiny residual driving expansion. How? Nobody knows. Some physicists have proposed that dark energy is dynamic, a field rather than a constant, one that changes its strength over time. This field has a name in theoretical physics: quintessence. If dark energy is a field, it had a value at the beginning of the universe, and that starting value may have been set in the pre-Bang era. A team analyzing data from the Dark Energy Spectroscopic Instrument released results in 2024, suggesting that dark energy may in fact be evolving, strengthening slightly over cosmic time. This remains preliminary, and the scientific community is still evaluating it. But if confirmed, it would mean dark energy is dynamic, which makes its initial conditions a question with a physical answer. That answer might live in the pre-Bang era. Some theoretical frameworks propose that the inflaton field, the energy that drove cosmic inflation, did not entirely dissipate during reheating. A tiny remnant persisted, cooling and diluting as the universe expanded, and is now observable as dark energy, an echo of the Bang's opening act, still pushing space apart billions of years later. If true, dark energy is a direct relic of the epoch closest to the Bang. Measuring it with enough precision becomes an indirect measurement of inflationary conditions, which in turn constrains what came before inflation. The most invisible force in the universe, one stretching all of space right now, may be the most direct evidence of the era before everything we know. And the data to test this is being collected right now by observatories designed exactly for this purpose. Look at the sky in one direction. Record the temperature of the ancient light coming from that point. Now look at the exact opposite direction, as far away from the first point as it is possible to look. The temperature matches to within 100,000ths of a degree. Those two regions of the sky are separated by roughly 93 billion light years. They are so far apart that even if signals had been traveling at the speed of light since the very first moment of the Bang, they would never have had time to reach each other. They have been causally disconnected since the beginning of the universe, and yet their temperatures are identical. This is the horizon problem, and it is one of the deepest unsolved puzzles in cosmology, because identical temperatures across disconnected regions imply that those regions were once in contact, sharing heat, reaching equilibrium, before they were separated. Standard inflation solves this elegantly. If the observable universe was once squeezed into a region far smaller than a proton, then all of it was in contact before inflation stretched it to cosmic scales. The uniformity is a memory of that pre-inflation contact. But inflation only pushes the problem back. Before inflation started, what set the initial conditions so uniformly that inflation could smooth them out into what we see? Some physicists argue the uniformity is evidence of a prior phase of the universe, a phase in which the entire observable cosmos was in thermal contact for an extended period before whatever transition produced the Bang. In bounce cosmologies and cyclic models, the pre-Bang phase would naturally allow this kind of equilibration. The previous universe, contracting toward the bounce point, would have homogenized over time, producing the smooth initial conditions that inflation then inherited. The ekpyrotic model offers a different explanation. As two membranes drift toward each other through higher dimensional space, quantum fluctuations on both surfaces average out. By the time the collision occurs, both surfaces are nearly uniform in energy. The collision transfers that uniformity into the hot plasma of the new universe. In each of these models, the smooth sky you see tonight is not an accident of the bang. It is a memory of something that happened before the bang, a period of contact, equilibration, or averaging that set the stage. The uniform temperature of the ancient light is both the strongest confirmation of the Big Bang and the clearest argument that the Big Bang alone is not enough to explain what we see. Something prepared the universe before the bang fired. And there are places in the sky where that preparation shows its seams. In 2004, scientists analyzing the cosmic microwave background released a map of unprecedented detail. The temperature variations were charted across the entire sky, producing a portrait of the infant universe that researchers expected to match the predictions of standard cosmology almost perfectly. In the southern sky, one feature stood out immediately: a region of the sky, roughly 5 degrees across, registering significantly colder than its surroundings. Cold enough to be statistically unusual. Cold enough that the probability of it appearing by random chance in a standard inflationary universe was calculated at around 1 in 1,000 to 1 in 50, depending on the method used. Astronomers called it the cold spot. The cold spot is real. It appears in multiple independent analyses of the cosmic microwave background data from both the Wilkinson Microwave Anisotropy Probe and the Planck satellite. Its existence is not in dispute. Its explanation is: the leading mainstream explanation is a giant void, a region of space with significantly less matter than average, whose gravitational effects cool photons passing through it. Photons lose energy climbing out of a gravitational well, and a large enough underdense region would produce exactly the kind of cold imprint seen. Surveys of the large-scale structure of the universe have identified a large void in roughly the direction of the cold spot. But the void, while large, may not be large enough or empty enough to fully account for the cold spot's magnitude. The debate among cosmologists is ongoing. A second explanation reaches further. Some physicists have proposed the cold spot is a bubble collision scar, the imprint left by an encounter between our universe and a neighboring bubble universe in an eternal inflation scenario. The collision would have compressed and cooled a region of our early universe, leaving a permanent mark in the ancient light. The predicted signature of a bubble collision is specific: a circular temperature anomaly with a distinctive profile, a sharp edge, and a polarization pattern in the surrounding cosmic microwave background that differs from standard fluctuations. Current data is not precise enough to confirm or rule out this signature. The Simons Observatory and future experiments are designed to measure the polarization of the cosmic microwave background at the sensitivity level needed to test this. If the cold spot is a collision scar, it is the most direct physical evidence of a multiverse ever found. A bruise left by a neighboring universe on the face of ours. And it sits in the southern sky right now, 5 degrees wide, ambiguous, waiting for an instrument sensitive enough to read its edges clearly. The cold spot is one anomaly. There is another, larger one, hiding in the way the entire sky seems to prefer a particular direction. In 2003, a team of physicists doing a detailed analysis of the cosmic microwave background noticed something that should not exist. The largest scale temperature patterns in the ancient light, the patterns that span the entire observable universe, were aligned with each other. They shared an orientation. They all pointed in roughly the same direction across the sky, a direction that happens to align with the plane of our solar system and the direction of the equinoxes. The statistical significance was high enough to be alarming. In a universe born from a random quantum event, there is no reason for the largest structures in the cosmos to prefer any direction at all. The universe, at the grandest scale, should look the same in all directions. This principle is so fundamental that it has a name: the cosmological principle. And the alignment appeared to violate it. One physicist called the alignment the axis of evil, a deliberately provocative name meant to signal how seriously problematic it was for standard cosmology. The scientific community's first response was skepticism about the analysis, but subsequent studies, including independent analyses using the Planck satellite's more detailed data, confirmed the alignment. The preferred direction is real. Several explanations have been proposed. The most conservative is contamination. Our galaxy emits microwave radiation, and if that emission was not perfectly removed from the data, it could leave an artifact aligned with the galactic plane. Multiple teams have worked to test this explanation. The alignment persists even after careful galactic foreground removal, though the debate over sufficiency of those corrections continues. A second explanation invokes anisotropic expansion. If the universe expanded faster in some directions than others, in its very earliest moments, that directional preference could imprint on the large-scale structure we see today. An anisotropic early universe contradicts the standard model, but fits within some alternative cosmologies. A third explanation reaches back before the Bang. If the pre-Bang state had a preferred direction, a spin, a flow, or a structural asymmetry, that orientation could have survived through the transition into our universe and imprinted on the largest scales, the ones formed first and affected most directly by the initial conditions. A rotating or directionally structured pre-Bang phase would leave exactly this kind of large-scale alignment, while leaving smaller-scale structures largely random, which is consistent with what we observe. The axis of evil remains unexplained. Multiple surveys of the large-scale structure of the universe, looking at the distribution of galaxies across billions of light-years, are building toward a picture detailed enough to test these explanations. The results will take years to accumulate, but the alignment is there. The universe at its largest scales knows which way is up, and that knowledge may have been inherited from before it was born. Something stranger than a direction is hiding in the data, and it has to do with the very concept of time. Everything discussed so far has smuggled in an assumption. We have been using the word before as if it has a clear meaning. Before the bang, before the bounce, before the collision. But time itself may have been created at the Big Bang. And if it was, the word before is grammatically valid but physically empty. This is not evasion. It is one of the most seriously held positions in theoretical physics, developed rigorously by Stephen Hawking and his collaborator James Hartle in the 1980s. Their framework is called the no-boundary proposal. Here is the core idea. In general relativity, time and space are not fundamentally different. They are both dimensions of a single four-dimensional fabric. Near a black hole, time and space partially swap roles. In the extreme conditions of the Big Bang, Hawking and Hartle proposed that time itself transitions into a spatial dimension. Picture the surface of the Earth. Every point on the surface has a latitude. If you ask what is south of the South Pole, the question makes no grammatical sense. The South Pole is the end of south. South runs out at that point. In the no-boundary proposal, the Big Bang is the South Pole of time. Time exists everywhere in our universe, just as south exists everywhere on Earth above the South Pole. But asking what happened before the Bang is asking what is south of the South Pole. The question dissolves. Time in this model emerged from a quantum geometry in which it had no sharp beginning, only a smooth, rounded origin where the dimension we call time gradually converted from something more like a spatial dimension into what we experience as the forward march of moments. The no-boundary proposal is mathematically rigorous and was developed by two of the most celebrated physicists of the 20th century. It remains a serious and respected framework. But it carries an implication that should stop you cold. If time began at the Bang, then causality, the principle that every event has a prior cause, also began at the Bang. Our entire notion of explanation of why things are the way they are depends on causes preceding effects. Strip away time's beginning, and you strip away the possibility of a cause for the Bang itself. The universe, in the no-boundary proposal, has no cause. It simply is. A self-contained, finite geometry with no edge, no boundary, no before. Many physicists find this intellectually satisfying. Others find it deeply unsatisfying because it places the origin of everything beyond the reach of explanation by definition. And here is where it gets philosophically vertiginous. Even within the no-boundary proposal, the quantum geometry from which our universe emerges had properties. It had a wave function. That wave function had a specific mathematical form that selected the smooth, low entropy initial conditions of our universe from among many possibilities. Something determined that form. Even if time had no beginning, the mathematical structure underlying the Bang did not emerge from nothing. It emerged from something, whether you call it a quantum geometry, a mathematical law, or a pre-existing framework. The question of what came before does not disappear. It transforms, and one physicist has transformed it into the boldest proposal of all. Roger Penrose has spent over 50 years thinking about the shape of time. He contributed to the mathematics of black holes, to the proof that singularities are unavoidable in general relativity, to the foundations of quantum mechanics. He shared the Nobel Prize in Physics in 2020, and in his 70s he published what may be his most controversial idea. Conformal cyclic cosmology proposes that the universe goes through an infinite series of eons. Each eon begins with a bang, expands, produces galaxies, stars, and eventually exhausts itself. Black holes dominate the far future. One by one, over timescales so vast, they dwarf the current age of the universe by factors beyond imagination. Those black holes evaporate through Hawking radiation. In the extremely far future, every black hole is gone. Every particle has decayed or settled into its lowest possible state. The universe is a cold, nearly empty sea of photons and a dwindling number of ultra-low energy particles. At this point, space is expanding so rapidly that all structure has dissolved. The universe approaches a state of perfect thermal equilibrium. Now, here is Penrose's mathematical insight. At that final state, something remarkable happens at the level of geometry. The only things remaining in the universe are massless particles like photons, and massless particles, traveling at the speed of light, do not experience time. They do not experience distance in the direction of travel. For a photon, the entire journey from one side of the universe to the other takes zero time and covers zero distance. In this limit, the dying universe loses its ability to define scale. Big and small become meaningless when everything moves at the speed of light and nothing has mass. And Penrose shows that when a system loses the ability to define scale, its geometry becomes mathematically identical to the geometry of a new Big Bang. The vast, cold, nearly infinite dying universe and the tiny, hot, dense starting point of a new universe are, in a specific and precise mathematical sense, the same geometry. One becomes the other. The death of one eon is the birth of the next, without any discontinuity in the underlying mathematics. There is no wall between eons. There is a smooth transition, and through that transition, some information survives. The Hawking points described in Chapter 1 are that surviving information, the evaporation of black holes in the previous eon, releases energy in spherical pulses. Those pulses imprint on the geometry of the transition. They arrive in the new eon as faint circular temperature patterns in the cosmic microwave background. Penrose and his colleagues have analyzed cosmic microwave background data and reported finding these patterns at statistical significance above what random variation would produce. Other teams dispute the interpretation. The debate is ongoing, but the framework is self-consistent, based on established mathematics, and makes specific observational predictions. And its implication is breathtaking. We are not the first universe. The Big Bang is not the beginning of everything. It is a seam in an eternal fabric, the stitch between one eon and the next. The cosmos is recycling itself across timescales so enormous that our universe's entire 13 billion year history is a single breath in an infinite cycle. The evidence for all of this is subtle, faint, written in the oldest light in existence, but one discovery in our own sky, one that has nothing to do with the cosmic microwave background, may be the most direct clue yet that something was here before us. The universe has a growth rate. Astronomers call it the Hubble constant, named after Edwin Hubble, who first measured the expansion of the universe in the 1920s. The value of this constant tells you how far space is stretching at a given scale, how quickly galaxies are moving apart from each other. Measuring it should be straightforward. Measure distances, measure velocities, divide, get a number. The problem is that two completely independent methods of measuring this number give different answers. The first method uses the cosmic microwave background. By studying the precise patterns in that ancient light and feeding them into the standard model of cosmology, Physicists calculate how fast the universe should be expanding today. This method gives a specific value. The second method uses standard candles, astronomical objects whose intrinsic brightness is known, allowing their distance to be calculated from how dim they appear. A particular type of star called a Cepheid variable and a type of stellar explosion called a Type 1a supernova are used as these candles. Measure enough of them, build a cosmic distance ladder, and read off the expansion rate. This method gives a different value. The two values disagree by enough that if the measurements were a dart game, the two darts would land several inches apart on a board where the bullseye is the width of a pencil tip. The discrepancy is now above 5 sigma in statistical significance. 5 sigma is the threshold physicists use to declare a discovery. The Hubble tension is real, it is measured, it is confirmed, and it has no agreed explanation. Many proposals have been offered. Early dark energy, a burst of extra energy in the universe's first moments that would alter the sound waves in the early plasma and shift the cosmic microwave background prediction. Extra relativistic species, additional lightweight particles that affected the early universe's expansion rate. Modified gravity, the idea that Einstein's equations need adjustment at cosmic scales. Each proposal has been tested against multiple datasets. None has cleanly resolved the tension without introducing new problems elsewhere. One category of proposals reaches back before the Bang. If the pre-Bang era set initial conditions that differ slightly from what standard cosmology assumes, those differences could propagate forward in time, showing up as a discrepancy between the early universe measurement and the late universe measurement. A pre-Bang contribution to the energy content of the cosmos could shift the cosmic microwave background prediction just enough to close the gap. These models are speculative, but they are being actively developed and tested. What is certain is this: the Hubble tension tells us the standard model of cosmology, as currently written, is incomplete. Something is missing. And the most compelling category of missing ingredient is something that operated before or during the very earliest moments of the Bang. Two telescopes aimed at different eras of cosmic history are giving different answers. The universe is contradicting itself. And that contradiction may be the most important clue yet that our picture of the beginning needs a chapter we have not yet written. What comes after the tension is stranger still, because the anomalies are not just in the numbers, they are in the structures, in galaxies that formed too early, too massive, and in places where they should not yet exist. The James Webb Space Telescope launched in December of 2021. Its primary mirror stretches nearly 22 feet across. It orbits nearly 1 million miles from Earth, beyond the Moon, at a point where the gravitational pull of the Earth and the Sun balance perfectly. Its mission was to see further back in time than any instrument before it. Light from distant galaxies takes billions of years to reach us, so looking far away means looking far into the past. Webb was designed to see the universe as it looked just a few 100 million years after the Bang, when the first galaxies were just beginning to form. What it found shocked the scientific community. Fully formed, massive galaxies present less than 300 million years after the Bang. Galaxies containing hundreds of billions of stars, structured, rotating, with defined shapes, appearing at a time when standard cosmology says the universe should have contained only diffuse clouds of hydrogen gas, and the first scattered, primitive stellar nurseries. Building a galaxy like the ones Webb found takes time. Stars must form, live, die, and seed the surrounding gas with heavier elements. Multiple generations of stars must cycle through before enough material accumulates to build the structures Webb observed. By the standard model's timeline, those processes should have required at least 1 billion years, probably more. Webb found the finished product at a fraction of that age. Some of these early galaxies are also surprisingly compact and dense, packing stellar mass into a region far smaller than similarly massive galaxies in the modern universe. Others show signs of already having supermassive black holes at their centers, black holes that in the standard picture take billions of years to grow. The scientific community's initial response was careful. Redshift measurements needed confirmation. Photometric estimates needed spectroscopic verification. That verification has been accumulating over 2 years of Webb observations, and the early galaxies are holding up. Several explanations are being tested, Perhaps star formation in the early universe was far more efficient than models assumed, converting gas into stars faster than current physics predicts. Perhaps dark matter clustered more densely in the early universe, accelerating the gravitational collapse that seeds galaxy formation. Perhaps the initial density fluctuations from inflation were stronger on certain scales than standard models calculate. Each of these explanations requires adjusting the standard model. None requires invoking a pre-bang error, but one class of explanation does. If the seeds of structure in the early universe were laid down before the bang, if the pre-bang state left enhanced density perturbations at specific scales, those seeds would have given early galaxies a head start. Structures would have formed faster because they began from a more advanced starting point, one prepared in the era before ours. Webb is finding anomalies faster than theorists can comfortably explain them. Each new data release adds to a growing ledger of early universe surprises. The telescope was built to confirm the standard model's predictions at the edges of the observable universe. Instead, it is finding a universe that grew up faster than it should have. A universe that looks in some regions of the early sky as if it had already been running before the clock started. And Webb has only been operational for a fraction of its planned lifespan. What it finds in the next decade will either cement the standard picture or force a rewrite of the first chapter of cosmic history. Einstein's general relativity predicts that accelerating masses produce ripples in the fabric of space-time itself. These ripples, called gravitational waves, travel at the speed of light and pass through everything, stretching and compressing space as they go. In 2015, the Laser Interferometer Gravitational Wave Observatory detected gravitational waves for the first time, produced by two black holes merging over 1 billion light-years away. The signal was a chirp, a fraction of a second long, and it stretched the detector by a distance roughly 1,000th the width of a proton. That was from two stellar mass black holes. The early universe produced gravitational waves on a far grander scale. If cosmic inflation occurred, the violent exponential expansion of space in the first fraction of the first second would have generated gravitational waves across all scales simultaneously. These primordial gravitational waves would be stretched by expansion to wavelengths spanning hundreds of millions of light-years today, far too long to detect directly with any ground-based instrument. But they would leave a specific imprint on the cosmic microwave background. When photons in the early plasma were scattered by these long gravitational waves, they acquired a particular pattern of polarization. Physicists call this the B-mode polarization signal. It curls in a specific way that distinguishes it from all other sources of microwave polarization. Detecting this signal would confirm inflation and, critically, measure its energy scale, which constrains which specific model of inflation occurred. Different models of inflation, including those with pre-bang connections, predict different strengths and spectra of primordial gravitational waves. The measurement would function as a direct probe of the energy conditions at the bang's first moment. The BICEP and Keck array experiments at the South Pole have been searching for this signal for over a decade, gradually pushing the sensitivity of their measurements. So far, they have established upper limits on the signal strength, ruling out the most energetic inflation models. The ekpyrotic model, the membrane collision scenario described in Chapter 8, predicts a primordial gravitational wave signal far weaker than standard inflation, potentially below the detection threshold of any instrument currently planned. If future experiments reach sufficient sensitivity and find no B-mode signal, it would strongly favor models like ekpyrosis over standard inflation. Meanwhile, pulsar timing arrays represent a separate approach. Pulsars are rapidly rotating neutron stars that emit radio pulses with extraordinary regularity, functioning as cosmic clocks. A background of very long wavelength gravitational waves would cause correlated variations in the arrival times of pulses from multiple pulsars across the sky. In 2023, multiple independent pulsar timing array collaborations announced evidence for exactly such a background signal. The signal is consistent with a stochastic gravitational wave background, a constant hum of gravitational waves from multiple sources overlapping across the entire sky. The source of this background is debated. Merging supermassive black hole pairs across cosmic history could produce it. So could cosmic strings, topological defects from early universe phase transitions. So could gravitational waves produced in the pre-inflationary era, or even at the moment of the bang itself? Distinguishing these sources requires more data, more pulsars, and longer baselines of observation. But the hum is real. The universe is vibrating, and some of those vibrations may be messages sent from the first fraction of the first second, or from before it. We are beginning to hear something. The question of what is speaking is the next frontier. Stephen Hawking showed in the 1970s that black holes are not perfectly black. They radiate, slowly, imperceptibly, but continuously. A black hole steadily loses mass through quantum effects at its event horizon, the point of no return, until eventually it evaporates entirely. This became one of the most celebrated results in theoretical physics. It also created one of the deepest problems. The radiation a black hole emits appears to be perfectly random, featureless thermal noise, carrying no information about what fell in. A book, a star, a human body, all destroyed, their specific atomic configurations apparently erased forever. But quantum mechanics has an absolute rule. Information cannot be destroyed. The state of every particle is encoded in a wave function, and wave functions evolve in ways that are mathematically reversible. If you could track every particle in the universe perfectly, you could always reconstruct the past. Information is conserved, always. Hawking's result seemed to violate this. Black holes swallow information and radiate featureless noise. The information vanishes. This is the black hole information paradox, and it occupied the minds of the greatest physicists alive for over 4 decades. The current leading resolution, still debated in its details, is that information is not destroyed. It is scrambled and encoded in subtle correlations within the Hawking radiation, in a form so complex it is practically unreadable. But physically present, the radiation is not truly random. It carries the ghost of everything that fell in. Now apply this to the Big Bang. If information is never destroyed, and if our universe emerged from a prior state through a bounce, a cycling, or some other transition, then the information content of the prior state did not vanish. It was encoded, scrambled, carried through the transition in some form. The Hawking points of Penrose's framework are one expression of this idea. The evaporation of black holes from the previous eon encodes information about those black holes into the geometry of the transition, which then appears in the cosmic microwave background of the new eon. But the information paradox resolution suggests something broader. The entire state of the previous universe, its matter distribution, its structure, its physical history, may have been encoded in the conditions of the bang, not legibly, not in a way we could ever reconstruct into a history of the prior universe, but physically present, shaping the initial conditions of ours. Our universe may be, in a deep and precise sense, the scrambled memory of everything that came before, the initial conditions that puzzled us in chapters 3 and 10, the low entropy, the fine-tuned constants, the uniform temperature, may all be aspects of that encoded memory, boundary conditions inherited from a prior state, rather than arbitrary settings selected from nothing. If true, we are not just inheritors of a Big Bang, we are inheritors of an entire cosmos, compressed and encoded into our starting conditions, invisible but physically real, the way a dream carries the emotional weight of a day even after the specific events are forgotten. And there is one more layer to this that has not yet been spoken aloud in mainstream physics, but sits at the edge of the most serious theoretical discussions. The implications reach not just backward in time, but forward, all the way to the fate of our own universe, and whether it too will leave a memory. The most radical idea about the beginning of the universe does not require a prior universe at all. It requires something stranger, a universe that was born from a quantum probability. In quantum mechanics, particles do not have definite positions or energies until they are measured. Before measurement, they exist in a superposition, a combination of all possible states simultaneously, described by a mathematical object called a wave function. The wave function gives the probability of finding the particle in any particular state when observed. What if the universe itself has a wave function? This idea was developed seriously by several physicists, most notably James Hartle and Stephen Hawking. with their no-boundary proposal from Chapter 15, and separately by Alexander Vilenkin in the early 1980s. Vilenkin's approach is called quantum tunneling from nothing. In Vilenkin's model, nothing means a state with no space, no time, no matter, and no energy. A state that classical physics says is completely stable because there is nothing to change. But quantum mechanics introduces a wrinkle. Even a state of absolute nothing has a wave function, and wave functions allow for quantum tunneling, the process by which a particle passes through a barrier it classically could not cross. Vilenkin calculated that the wave function of nothing has a small but non-zero probability of tunneling into the wave function of a small, closed universe. And once a small, closed universe with the right quantum numbers exists, it can inflate and expand into everything we see. The universe was born from a quantum fluctuation in absolute nothing. This is an extraordinary claim, and its critics have pushed back hard. The concept of nothing is philosophically and mathematically treacherous. Vilenkin's nothing still has quantum mechanics operating within it, which means it already has mathematical structure, physical laws, a framework. Whether that constitutes true nothing is a question without a clean answer. Hawking's no-boundary version sidesteps this by saying the question of a creator or a prior state is simply ill-formed. The universe's wave function describes a self-contained geometry with no boundary, no edge, and no prior cause. It simply exists, in the same way that a mathematical truth simply exists. Both approaches make testable predictions about the shape of the early universe's wave function, which translates into predictions about the spectrum of fluctuations in the cosmic microwave background. Those predictions can be compared against data. Current data is consistent with both approaches, but not precisely enough to distinguish them. Next-generation cosmic microwave background experiments and gravitational wave detectors will tighten the constraints. What both approaches agree on is striking. The universe's initial state was selected by quantum probability, and that probability distribution had a specific, calculable form. The universe did not begin at random. It began at the most probable quantum state consistent with the laws of physics. Those laws, in turn, had to exist before the universe began, or simultaneously with it, or be the universe in some fundamental sense that physics has not yet articulated. The hardest question in cosmology is not what came before the bang. It is why there are physical laws at all, why mathematics describes reality, and where those laws were before reality existed to obey them. Every black hole in our universe contains a singularity, a point of infinite density at its center, where the known laws of physics break down, identical in structure to the singularity at the Big Bang. This parallel is not accidental, and it has led physicists to ask a provocative question. If the Big Bang resembles the interior of a black hole, could our universe have been born inside one? Lee Smolin, a theoretical physicist at the Perimeter Institute, developed this idea into a full framework in the 1990s, calling it cosmic natural selection. His proposal works as follows. When a black hole forms in our universe, the extreme conditions at its center may not produce a true singularity. Following the logic of loop quantum cosmology from Chapter 6, the collapse reaches a minimum scale and bounces, producing a new region of space-time that expands into a new universe. That new universe is causally disconnected from ours. It exists in its own space-time, invisible to us, unreachable by any signal we could send. Each black hole in our universe is, potentially, the birth event of a child universe. And here is where Smolin's idea becomes genuinely biological in its logic. The child universe inherits the physical constants of its parent, but with slight random variations similar to genetic mutation. If those constants are compatible with the formation of stars and black holes, the child universe will itself produce black holes, spawning more child universes. If the constants are incompatible with black hole formation, the child universe produces no offspring. Over many generations of universes, the constants that promote black hole formation become dominant, selected for by a process directly analogous to natural selection. And it turns out that the constants that maximize black hole production are very similar to the constants that allow for complex chemistry and life. We may exist because universes that produce beings like us also happen to be the most reproductively successful universes. Smolin's framework makes a testable prediction. If it is correct, our universe should be near optimal for producing black holes. Adjusting any of its constants should reduce the total number of black holes that form over the universe's lifetime. This prediction has been partially tested and has not yet been falsified. Though the testing is difficult and ongoing, the framework also implies that our universe had a parent, a universe that existed before ours, in which a black hole formed, and in whose interior the conditions for our Big Bang were created. That parent universe may have had a parent, and so on, stretching back through an evolutionary tree of universes, across time and causality. We are not at the root of that tree. We are one branch, shaped by every universe that came before, carrying in our physical constants the accumulated heritage of a cosmic lineage. And somewhere in the observable sky, every black hole we have ever catalogued may be a birth canal into another branch of that tree. In the first fraction of the first second, the universe made a series of choices. It chose how strong gravity would be relative to electromagnetism. It chose the mass of the Higgs boson. It chose to favor matter over antimatter by a razor-thin margin. These choices are called symmetry breakings, and they are among the most consequential events in the history of reality. When the universe was at its highest temperatures, all the fundamental forces were unified into a single force with perfect symmetry. As the universe cooled through specific temperature thresholds, that symmetry shattered, the way ice crystals suddenly snap into a rigid pattern as water cools below freezing. Each shattering separated one force from the others and locked in the physical constants governing that force. The pattern of symmetry breaking is precise and documented. The electroweak force split from the strong nuclear force at around 10 to the power of 15 times the energy of a proton. Electromagnetism split from the weak force when the Higgs field switched on, at around 1,000 times the energy of a proton. Each split left behind a fossil, a difference in the strengths and ranges of the resulting forces, encoded in the masses of the particles that carry them. Those fossils are the physical constants we measure today. Now consider what this means for the pre-bang question. The pattern of symmetry breaking is determined by the starting temperature and the specific way the unified force's symmetry was arranged at the bang's first moment. A different starting arrangement would produce different breakings, different constants, a different universe. In cyclic models, the symmetry structure of the previous eon's final state would influence the starting conditions of the next bang. The symmetries inherited through the transition would constrain which breakings occur, and how. The constants of our universe may be downstream of symmetry choices made in a prior eon. In the ekpyrotic model, the brain collision energy determines the starting temperature, and the symmetry structure of the brain's field configuration at the moment of collision determines how the forces break apart in the new universe. The shape of reality was set by the shape of the collision. There is one symmetry breaking that stands above all others in its strangeness: the matter-antimatter asymmetry. When the forces broke apart in our universe, they produced slightly more matter than antimatter, roughly one extra matter particle for every billion matter-antimatter pairs. Those billion pairs annihilated, leaving behind radiation. The one survivor from each billion is every atom that exists today, every galaxy, every star, you. The source of that 1 in a billion imbalance is one of the greatest unsolved problems in physics. The standard model of particle physics does not predict an asymmetry large enough to explain what we observe. Something extra produced the excess matter. That something may have operated before or during the bang's first moments, and its fingerprint may be sitting in the asymmetry of the universe we inhabit, waiting to be read. There is a number in physics so embarrassingly wrong that it represents the worst prediction in the history of science, and it sits at the heart of the pre-bang mystery. When physicists apply quantum field theory to empty space, they find it should be filled with energy. Virtual particles pop in and out of existence constantly, borrowing energy from the quantum vacuum and returning it on timescales too brief to violate any physical law. This vacuum energy is real. It has been measured indirectly in laboratory experiments. It is not a theoretical artifact. But when you add up the contributions from all the quantum fields, The number you get for the energy density of empty space is roughly 10 to the power of 120 times larger than what we actually measure through the acceleration of the universe's expansion. 1 followed by 120 zeros. That is the ratio of the predicted vacuum energy to the observed dark energy density. Physicists call this the cosmological constant problem, and its scale is genuinely disorienting. Every other prediction in quantum field theory matches observation to extraordinary precision. This one misses by the largest margin ever recorded in any scientific field. The most natural interpretation is that something is cancelling almost all of the vacuum energy with extraordinary precision, leaving only a tiny remainder. The problem is that no known physical mechanism performs this cancellation. The cancellation would have to be tuned to 120 decimal places. Several explanations have been proposed over decades. Supersymmetry, a hypothetical symmetry between matter and force particles, would naturally cancel the vacuum energy contributions if it were exact. But supersymmetry, if it exists, is broken, meaning the cancellation is imperfect. The Large Hadron Collider has searched for supersymmetric particles across the energy range where they were expected to appear, and found nothing. The anthropic explanation applies the multiverse. In a landscape of universes with different cosmological constants, only those with a small but non-zero value allow for the formation of galaxies, stars, and observers. We measure a small value because we exist only in universes where it is small. The pre-bang explanation is more specific. Some cyclic models predict that the cosmological constant decreases with each cycle of the universe, as the transition between eons dilutes it. If we are deep into a sequence of cycles, the value has been suppressed by the accumulated history of prior eons, producing the tiny residual we observe today. If this is correct, the absurdly small value of dark energy is a historical record. The smaller it is, the more cycles have passed before ours. Our universe's cosmological constant is a counter, incrementing downward through cosmic time, and we have read its current value. We know the number. What we do not yet know is how many cycles produced it. Every cubic centimeter of empty space seethes with activity. Quantum field theory describes every particle in the universe as an excitation of an underlying field that permeates all of space. An electron is a ripple in the electromagnetic field. A photon is a ripple in the electromagnetic field. Every point in space contains all of these fields simultaneously, even in regions where no particles are present. In their ground state, these fields are not still. They fluctuate. Pairs of particles and antiparticles appear and vanish faster than any instrument can measure. Their existence permitted by the Heisenberg uncertainty principle, as long as they return their borrowed energy before time runs out. The space around you is filled with this invisible quantum foam. This vacuum fluctuation is measurable. Place two metal plates very close together in a vacuum, and they will be pushed toward each other by a force with no classical explanation, the Casimir effect. Quantum fields outside the plates fluctuate at all wavelengths. Between the plates, only fluctuations with wavelengths that fit between them are permitted. The mismatch in pressure pushes the plates inward. The vacuum pushes things. Now scale this up to cosmological dimensions. Inflation theory relies on a quantum field, the inflaton, to drive the exponential expansion of the early universe. As inflation proceeds, quantum fluctuations in the inflaton field get stretched from subatomic scales to cosmic ones. These stretched fluctuations become the density variations that seed all of the large-scale structure in the universe. The galaxies, the cosmic web, everything we see originated as quantum noise in a field. Vilenkin's tunneling from nothing proposal takes this further. The entire universe may have been a quantum fluctuation, a spontaneous appearance of space-time from a quantum vacuum state, driven by the same underlying uncertainty that generates virtual particles in every cubic centimeter around you. The difference in scale is enormous, but the physics is the same. If this is the correct picture, then the question what came before the Big Bang has a quantum mechanical answer. Before the Bang, there was a quantum vacuum state, a sea of probabilistic potential, no particles, no space-time, no matter, but a mathematical framework describing all the ways a universe could come into being. That state is not nothing. It has structure, it has rules, it has a wave function. Physicists have spent decades arguing about whether a quantum vacuum state constitutes true nothingness or a form of being. The answer may matter less than what the vacuum state implies. Creation is not a unique event that happened once. It is a process that the laws of quantum mechanics allow, perhaps demand, to happen wherever the conditions are right. Our universe may be one of countless events of creation, scattered across a quantum void, each one a ripple in a field that has no center, no edge, and no beginning in the way we usually mean, and each one leaving behind, in the structure of its own cosmic microwave background, the faint imprint of the quantum conditions from which it emerged. String theory is the most mathematically ambitious framework in the history of physics. It proposes that every particle, every force, every dimension of reality emerges from the vibrations of tiny, one-dimensional strings of energy, interacting in a space of 10 or 11 dimensions. The extra dimensions are real in the theory's mathematics. They are simply curled up at scales far below anything currently measurable, rolled into geometrical shapes called Calabi-Yau manifolds. The specific shape of these curled dimensions determines the physical constants of the universe that strings inhabit. And here is the staggering implication. The number of possible Calabi-Yau shapes is not small. Estimates put it at roughly 10 to the power of 500 distinct configurations, each producing a different universe with different physical constants, different particle masses, different force strengths. 10 to the power of 500 is a number so incomprehensibly large that the total number of atoms in the observable universe is insignificant by comparison. The observable universe contains roughly 10 to the power of 80 atoms. String theory's landscape of possible universes outnumbers atoms in our cosmos by a factor, with 420 additional zeros in the exponent. Each configuration in the landscape is, in principle, a valid universe. The question of which configuration we inhabit becomes, in this framework, a question of cosmic history. Our universe sits at one point in the landscape because of the specific way its extra dimensions curled up during the cooling after the bang. How those dimensions curled was determined by the energy conditions at the bang's first moments, and those conditions were, in various pre-bang frameworks, set by the prior state. In the ekpyrotic model, the shape of the extra dimensions before the brane collision determines which landscape point the new universe occupies. The prior state of the brane selects our physics. In cyclic models, the way extra dimensions evolve through the transition between eons determines the constants of the next eon. Each cycle may produce a different point in the landscape, or the landscape may be navigated in a specific path determined by the physics of the transition. String theory's landscape has been criticized as unpredictive because with 10 to the power of 500 options, it seems possible to accommodate any observation by pointing to some region of the landscape where it would be natural. This is a genuine and serious criticism. But the landscape also implies something profound. The constants of nature are contingent. They are the outcome of a historical process, and the history that determined them extends back before the bang. Our universe's physics is not necessary. It is selected, and the selector may have been everything that came before. You remember the past. You do not remember the future. Causes precede effects. Eggs break, but never unbreak. These facts feel so obvious, so fundamental, that questioning them seems absurd. But the microscopic laws of physics are time-symmetric. Every equation governing the motion of particles works equally well running forward or backward. If you filmed a collision between two billiard balls and played it in reverse, it would look perfectly physical. The laws of mechanics do not care which direction time runs. So why does the universe have a definite direction? Why does time have an arrow? The answer, physicists agree, is entropy, the second law of thermodynamics, introduced in Chapter 3. Disorder increases. Time runs in the direction of increasing entropy, but this just pushes the question back. Entropy increases because the universe started in a very low entropy state. If the initial state had been high entropy, time's arrow would point in no particular direction, or differently, or not at all. Why did the universe start with such a precise, low entropy state? That question, first introduced in Chapter 3, becomes even more unsettling here, because the answer to why time has a direction, why you remember the past rather than the future, why cause precedes effect in your experience of reality, is the same as the answer to why the Big Bang had the specific initial conditions it did. Your experience of time flowing forward is a direct consequence of the improbable starting conditions of the cosmos, and those starting conditions, as argued throughout this journey, may have been set by whatever came before. In Penrose's cyclic model, the arrow of time in our universe is a consequence of the transition between eons. The previous eon ended in maximum entropy, which through the conformal transformation becomes the minimum entropy starting point of the next eon. The arrow of time resets at each transition, pointing away from the moment of maximum compression and toward the expanding future. In bounce cosmologies, the pre-bang collapsing universe had its own arrow of time pointing inward toward the bounce. Our universe's arrow points outward from the bounce. Two eras of time with arrows pointing in opposite directions, separated by the moment of maximum compression. If this is correct, the universe that preceded ours experienced time in the opposite direction from us. Its future was our past. Its memories were of events that, from our perspective, happened after the bang. Time's arrow is not a fundamental feature of the universe. It is a local orientation defined by the entropy gradient in each era. And the boundary between eras, the bang itself, is the point where the arrow flips. Your sense of time moving forward, the feeling of momentum carrying you from past to future, is a thermodynamic gradient inherited from the bang, which was inherited from whatever came before. The direction of your experience is a fossil, and the fossil points back toward the seam between universes. Every story eventually ends. Ours will too. The far future of the universe is not uncertain in its broad outlines. Physics gives us a clear picture, and it is vast in its timescale and deeply strange in its detail. Over the next few trillion years, star formation will gradually exhaust the gas reservoirs of galaxies. New stars will stop forming. Existing stars will age, die, and leave behind white dwarfs, neutron stars, and black holes. The galaxies will dim. The universe will grow darker with every passing eon. Over time scales measured in numbers with dozens of zeros, protons may decay, dissolving the last atomic matter into radiation and leptons. White dwarfs and neutron stars, losing the matter they are made of, will fade and disperse. What remains will be black holes. Increasingly isolated in an accelerating, expanding universe, the black holes will be the last structures in existence, and they will evaporate. Hawking radiation is the mechanism. A black hole the mass of our star takes approximately 10 to the power of 67 years to evaporate completely. A supermassive black hole at a galaxy's center takes 10 to the power of 100 years. These timescales are so far beyond the current age of the universe that they essentially require new vocabulary. After the last black hole evaporates, the universe enters the state Penrose calls the final epoch, a sea of photons and ultra-low energy particles spreading outward through an accelerating expansion, growing thinner and cooler without limit. In the framework of standard cosmology, this is the heat death of the universe, maximum entropy, the end. In Penrose's cyclic framework, it is something else entirely. The mathematical transformation described in Chapter 16 applies at this exact state. The geometry of maximum entropy, where scale loses meaning, smoothly connects to the geometry of minimum entropy at a new bang. And the black holes that evaporated, each one sending its Hawking radiation outward in spherical pulses across cosmic time, leave those pulses encoded in the geometry at the transition point. They become the Hawking points in the next universe's cosmic microwave background, the memory. Our universe is right now creating the fossils that the next universe will spend its own history trying to decode. Every black hole we have ever observed, every supermassive core at the center of every galaxy, is a future message being slowly composed. Its transmission will take longer than the current age of the universe, by factors too large to write out. But it will be sent, and somewhere in the future cosmos, beings we cannot imagine will look at their oldest light, find faint circular patterns, and argue about what left them. They will be reading us. There is a question hiding underneath every chapter of this story. It has been present since Chapter 1, patient, waiting for the right moment. Where did the laws of physics come from? Every model of the pre-Bang era assumes physics was operating. The bounce requires quantum mechanics. The brane collision requires string theory. The quantum tunneling requires a wave function and probability amplitudes. Even Penrose's conformal transformation is a mathematical operation that must be valid for the scenario to work. All of these frameworks carry physical laws that existed before, during, and after the universe. The laws are not created by the universe. They are not contained within it. They are external to it, more fundamental than it, the framework within which even the Bang itself occurred. This raises a possibility that most physicists regard as outside their professional jurisdiction, but that some of the most serious thinkers in science have grappled with directly. The physicist Max Tegmark developed what he calls the mathematical universe hypothesis. His proposal is precise and radical. Mathematical existence and physical existence are the same thing. Every mathematically consistent structure exists, physically, as a universe. Our universe is one mathematical structure among all possible mathematical structures, and we inhabit it because we are part of it, the way a character in a novel is part of the novel's narrative structure. In this view, asking what came before the Big Bang is asking what mathematical structure preceded ours. The answer is that mathematical structures do not precede each other in time. They simply exist timelessly in a Platonic landscape of all possible mathematics. Our Bang was a transition between mathematical regimes, a phase change in the structure of the active equations, and what came before was a different region of the same mathematical landscape. This framework resolves the fine-tuning problem completely. Every combination of constants exists in some universe. We observe our particular set because we exist in our particular mathematical structure. No design is required. No selection. Every possibility is equally real. Tegmark's hypothesis is by design untestable in the usual sense. It predicts that all possible universes exist, which makes no specific prediction about which universe we should find ourselves in, beyond the requirement that it supports observers. But it offers something the other frameworks struggle with. It answers the question of where the laws came from. They did not come from anywhere. They exist the way mathematical truths exist, necessarily, without cause, without origin, without a moment before which they were absent. 2 + 2 = 4 before the Big Bang. It will equal 4 after the last black hole evaporates. The truth of mathematics requires no universe to house it. If physical laws are mathematical truths, they are similarly eternal. The Bang was not the beginning of the laws. It was the laws expressing themselves in a new configuration. What came before the Bang was the same thing that exists right now, underlying every particle, every force, every moment of time. Mathematics itself. There is one more framework that physicists mostly refuse to discuss professionally, but that follows logically from the multiverse and the mathematical universe ideas. If the laws of physics are mathematical, and if mathematical structures can give rise to conscious observers, and if sufficiently advanced civilizations could simulate universes with their own physical laws, then the number of simulated universes in any sufficiently old cosmos would vastly outnumber the one original physical universe. The argument, developed rigorously by philosopher Nick Bostrom and examined seriously by physicists including Neil deGrasse Tyson, runs as follows. An advanced civilization with enough computing power could simulate billions of universes. Each of those simulated universes might itself contain civilizations capable of simulating more universes. After enough generations of simulation, the ratio of simulated realities to base reality approaches infinity. If that ratio is even modestly large, then the probability that any given conscious observer is in the base physical reality is essentially zero. Almost every experience of consciousness happens inside a simulation. This is a probabilistic argument, and it has the uncomfortable property of being very difficult to refute without making assumptions about the nature and limits of computation. For the pre-Bang question, the simulation hypothesis offers a distinctive answer. What existed before the Big Bang was the computing substrate running the simulation. Our Bang was the initialization of a program. The physical laws we observe are the rules encoded in that program. The fine-tuning problem dissolves because a programmer set the parameters for the reasons programmers set parameters, because those were the values they wanted. The simulation hypothesis makes almost no testable predictions, which places it in the same epistemological category as some multiverse proposals. But one potential signature has been identified. Any simulation running on a finite computational substrate must make approximations. At sufficiently small scales, those approximations might produce artifacts, regularities, or lattice-like structures in the fabric of space-time that would be invisible at larger scales, but present at the Planck scale. Current experiments cannot probe the Planck scale. Future developments in quantum gravity phenomenology might, in principle, reach energies where these artifacts would appear. Whether the programmer who initialized our bang exists in a physical universe subject to its own pre-bang questions, or in a mathematical substrate with no physical story at all, is a question that recursively applies to every level of the hierarchy. The simulation hypothesis does not escape the pre-bang problem. It defers it. Wherever the programmer lives, they too may be asking what came before their own beginning. Every answer reveals another layer. Every layer contains a universe. Every universe has a before. Every idea explored in this story makes contact with reality in at least one place. The pre-bang question is not purely philosophical. It is increasingly scientific, and the next 2 decades of observations may settle several of its central disputes. The Simons Observatory in Chile, currently being commissioned, will measure the polarization of the cosmic microwave background, with sensitivity roughly 10 times greater than the Planck satellite. It will search for the B-mode polarization signal from primordial gravitational waves, constraining the energy scale of inflation and distinguishing between inflation models with and without pre-bang connections. It will also look for the specific polarization signatures predicted by bubble collision events in the multiverse scenario. The CMB Stage 4 experiment, a planned array of telescopes across the South Pole and Chile, will push this sensitivity further, potentially detecting the inflationary gravitational wave background, down to levels predicted by the simplest inflation models. If it finds nothing at those levels, the ekpyrotic and bounce scenarios gain significant support. The Laser Interferometer Space Antenna, a space-based gravitational wave detector planned for launch in the mid-2030s, will detect gravitational waves at frequencies impossible to measure on the ground. Its sensitivity range covers signals produced by phase transitions in the early universe, cosmic string networks, and potentially pre-inflationary gravitational wave backgrounds. Each of these sources carries specific spectral signatures distinguishable from the others. The Square Kilometre Array Radio Telescope, under construction in South Africa and Australia, will massively expand pulsar timing array sensitivity. By monitoring thousands of pulsars simultaneously, it will characterize the stochastic gravitational wave background detected in 2023 with enough precision to identify its source, and potentially detect subdominant components from the very early universe or pre-bang era. The Roman Space Telescope and the Euclid satellite will map the large-scale structure of the universe across billions of light-years with unprecedented detail, constraining dark energy's evolution over cosmic time, testing whether its behavior is consistent with a simple cosmological constant or a dynamic field with pre-bang initial conditions. The James Webb Space Telescope continues to observe. Every season of data adds to the catalogue of early universe galaxies whose formation timeline must be explained. If the anomalies described in Chapter 18 persist and deepen, the pressure on standard cosmology will grow, and ongoing searches in the cosmic microwave background data for Hawking points, bubble collision signatures, the axis of evil's physical origin, and the cold spot's edge profile continue with every new analysis. Every one of these experiments is already funded, under construction, or operational. The tests are real. The timeline is concrete. Physics is closing in on the pre-bang era from multiple directions simultaneously. The question is not whether we will learn more. The question is how much we will learn before the answer forces a complete rewrite. There is a horizon in space, not a physical barrier you could touch, but a limit imposed by the finite speed of light and the finite age of the universe. Light from beyond, roughly 46 billion light-years away, has not had time to reach us. That region exists. We simply cannot see it. The pre-bang era imposes a harder limit. Even in the most optimistic cyclic or bounce models, the transition between eons is a period of extreme physics that scrambles information. The thermodynamic processing of the bounce, the conformal transformation of Penrose's model, the brain collision of ekpyrosis, all of them take the specific detailed state of the prior era and compress it into the boundary conditions of the new one. Some information survives. The Hawking points, if real, carry information about individual black holes from the prior eon. The initial entropy state carries information about the prior era's final conditions. The physical constants carry information about the prior era's symmetry structure, but the vast majority of the prior universe's specific history is gone. The detailed positions of its stars, the histories of its civilizations if it had any, the specific sequence of its events are compressed beyond any practical recovery. Reading a prior universe's history from the signals it left in ours is like trying to reconstruct a novel from the heat released when the book burned. Some physicists argue this limit is absolute, that no matter how sensitive our instruments become, the pre-bang era is irretrievably opaque beyond its statistical signatures. Others argue that quantum information conservation guarantees that, in principle, all information from the prior era is encoded in our universe's state, recoverable with infinite computational resources. In practice, the distinction matters less than it sounds. Infinite computational resources are not available. The information, even if present, is encrypted at a level that exceeds any foreseeable technology. What we can know is the shape of the pre-bang era, its thermodynamic state, its symmetry structure, its gravitational wave spectrum, whether it had a preferred direction, whether it was cyclic or singular, whether it was one universe or a field of many. What we cannot know, almost certainly, is its specific content, whether beings lived there, whether they knew what was coming, whether they too looked at the oldest light in their sky and wondered what came before. The questions we can answer are extraordinary enough. The questions we cannot answer are humbling. Both are part of what makes cosmology the most honest of the sciences. It tells you exactly where the map runs out. And what sits at the edge of the map is not emptiness. It is the acknowledgement that the universe is larger, older, and stranger than our instruments can fully reach. Every tool we have built to look at the universe, every satellite, every radio array, every gravitational wave detector, every space telescope has found something the standard model of cosmology did not fully predict: the Hubble tension, the early massive galaxies, the cold spot, the axis of evil, the stochastic gravitational wave background, the anomalous alignments in the oldest light, the improbably low entropy of the beginning, the absurd fine-tuning of the cosmological constant, the precise smoothness of a sky that should be patchy. Each of these anomalies, standing alone, might be noise, a statistical fluctuation, a measurement artifact, or a gap in technique, but they do not stand alone. They form a pattern, a consistent set of surprises, all pointing in the same direction. The universe did not begin cleanly. Its birth carries marks that the bang alone did not produce. Something shaped the starting conditions. Something smoothed the temperature across regions that should never have communicated. Something left circular patterns in the oldest light. Something gave the early universe a preferred direction. Something seeded structure faster than 13 billion years of expansion can fully account for. That something existed before the Big Bang. The evidence for this is not a single discovery. It is a convergence, multiple independent lines of observation, developed by different teams using different instruments, analyzing different aspects of the cosmos, all pointing at the same gap in our understanding. Roger Penrose's mathematics provide one framework for filling that gap. Loop quantum cosmology provides another. Eternal inflation provides another. The ekpyrotic model provides another. Quantum tunneling from nothing provides another. Cosmic natural selection provides another. These frameworks differ dramatically in their details and predictions. Some will be ruled out by the experiments described in Chapter 31. Others will survive. Perhaps one will be confirmed. Perhaps a new framework, not yet conceived, will emerge from the data and unify what the others only partially capture. But the underlying conclusion shared across all of these models is the same. The Big Bang was not the beginning of everything. It was a transition, a seam in a larger story, a boundary condition imposed by whatever came before. You have spent this time traveling from the familiar, the oldest light in the sky, to the genuinely strange mathematical universes. dimensional membranes, quantum tunneling from absolute nothing. That journey is not a journey into fantasy. Every stop along the way is rooted in published, peer-reviewed, actively debated physics, conducted by scientists at the most respected institutions on Earth. The question of what existed before the Big Bang is no longer the exclusive territory of philosophers and mystics. It is a scientific question, with testable answers closing in from multiple directions. The evidence is already in our hands. The instruments to read it more clearly are already being built. The generation of physicists who will settle this question is already alive, already working, already looking at the same sky you can see tonight. Something was here before the bang. It left fingerprints on everything, and we are reading them.